Okay, good morning. So I will continue on the same topic, and we'll talk about of asteroid observations as supporting space missions and what kind of role not plays there. So yeah. So just a general statement first. I mean, asteroids are studied for typically three reasons. One of these reasons is the desire to understand the formation and evolution of the solar system and whatever it contains. The second one is to mitigate hazardous impacts, and we have heard about these two topics during the past few talks. But then the third point is to utilize, if you want to prepare for utilizing resources in asteroids, then we also need to study them. And the point I'm trying to make with all of this is that these should not be seen as different things. I mean, as we've heard actually several times already, the same people who study any one of these parts are also basically contributing to another part. So an example is if you want to, the big open question, for instance, in asteroids or asteroid science is what's inside of the asteroids. We heard from Jane Liu about this, that there is maybe much more water in the asteroid belt than anybody has guessed for a long time. And of course, whatever the asteroids contain relates to all of these purposes to study asteroids. So it's not like one or the other, but it's like you're always contributing to all of these fields simultaneously. For the space missions, as with many space missions, most of them require ground-based follow-up in some sense, follow-up or not necessarily even follow-up, but characterization before the mission. So therefore, observing campaigns are usually arranged around all space missions that have some sort of asteroid component. And this is necessary both for optimizing this mission and instrument design and configurations, but also for maximizing the scientific return of the mission. And participating in these observing campaigns is basically often a gate to participating in the mission itself, even though you don't necessarily provide instrumentation or hardware or other software, etc., to the mission per se. But this sort of is a ticket to the mission. So that's why it's interesting for people also outside of those contributing with space tech. So I will now show just samples of what we have been working on that are related to space missions and that are related to the NOT. And one of these missions is the Psyche mission. It's a NASA mission that will launch later this year, I think, to Asteroid 16 Psyche, and this is an artist concept of what it looked like. People have usually thought that this is maybe a metallic asteroid because of its radar albedo in particular, but also its spectral classification based on optical spectra. And of course, if it would be a metallic asteroid, then its mass should be quite significant, and especially density then should be quite significant. So what we did was we have devised, not just for this object, but for more general purposes, a method for estimating asteroid masses. So what we basically do, we have the target asteroid that we're interested in, and then we track smaller sort of test asteroids that go past this. By measuring their positions over time, we can see how much the trajectory changes as a result of a close encounter. This, of course, is a simplification, so we don't actually do these kinds of analytical computation. It's like a numerical integration of all these particles involved. And what we basically predicted here in one of our papers was that along this time, so this is in MJD, so basically just dates starting from somewhere, and then this is the offset or uncertainty in right ascension. And we saw that, okay, at this date there is a significant uncertainty in the position of this test asteroid, and we observed that with NOT, and these measurements here are the NOT measurements So that it was sort of the correct solution was more towards the negative uncertainty region. And then we derived a mass estimate for this asteroid, which is somewhere around or a bit less than 4 grams per cc, which basically shows that it cannot be a solid metal, then its mass should be around 7 or 8 grams per cc. This same the same methods we also want to apply to the Gaia mission, or products produced by the Gaia mission, which is, as you probably know, it's this scanning space observatory producing highly accurate astrometry. Here you see the residuals from the data release 2 of asteroids, and you see that on the along scan direction we get hugely or very accurate observations in the range of milliarc seconds, whereas then across the across direction from the scan it's less accurate. So this is like, let's say, bad ground-based accuracy. But then of course, so you have this very or strongly correlated measurements. We can then put in these to this asteroid mass estimation code, and this is now just for a asteroid. I've actually now again forgot to put in the name of this asteroid, but it doesn't really matter. What I want to show is, here's if you look at the mass distribution produced, this purple is for Earth-based data. Gaia at this time did not yet produce enough astrometry, so it produced too little to really constrain the mass for this asteroid. But if you combine Gaia with ground-based data, then you get this very well constrained peak, and that will allow you already to start telling something about the interior structure and composition of this object. So a combination again with Gaia with ground-based could produce a lot more asteroid or useful asteroid masses and densities than what we have expect. So the expectation is, in round numbers, that we will get at the end of the Gaia mission, we will have about 100 asteroid masses with an accuracy of better than 10% or so. But of course, if we combine them with ground-based data, then we can produce much more. Another mission is the JAXA's Destiny Plus mission, which will do a flyby of asteroids Phaethon and 2005 UD. The question there is, Phaethon is interesting because it sort of lights up or becomes active very close to the perihelion, and it's not really well understood what the exact physical mechanism is that triggers it. So this is the perihelion date when it is active compared to the template star. The day before it was not active, and the day after it is still active, but it sort of dies off fairly soon after. And it's also linked to the Geminids. The path of the Destiny mission is shown here, and you also have the orbits of 2005 UD, which is also potentially associated with Phaethon. And this is one question that we've had. I mean, their orbits are reasonably similar, their spectral types are similar, but then we can also look at the polarimetric properties, and this basically shows that their polarimetric phase curves are almost identical. So this is another piece of evidence suggesting that these asteroids actually belong together. And then there is also this weird thing with Phaethon's polarization, that it appears to change from year to year. So here's the data from 2016 and then 2017, and they show sort of different trends at high phase angles. And we actually obtained polarimetry later on from this sort of branch, or when it showed basically the same hemisphere. That has unfortunately not been put through all of the analysis yet, so I don't have those results yet. But basically, we have from a different study with IR data shown that the fraction of light coming from different hemispheres is different from on these two dates. And that might actually explain it, why the polarization ratios are different. So they're basically looking at different hemispheres of the object, and these different hemispheres have different properties, surface properties. I will actually, I think, jump over this and just to mention, this is living its own life now. No, I should not be there. So just to mention something, which is coming up, the DART mission that will impact the Dimorphos asteroid orbiting asteroid Didymos. This is again a planetary defense mission that you might have heard of. So this will happen later this fall, and then a few years after there will be an ESA mission, Hera, and with its 2 CubeSats, it will go into the system and check what actually happened in the system. What we want to do from the ground during the mission, during the impact, is to actually, so here you have a model of the impact and the dust coming off. We want to, first of all, measure the change. So this is sort of mutual events, so eclipses or occultations by these 2 bodies. We can measure how the orbital period of this moon changes as a result of this impact. This is something that we want to do and have done with the NOT observing these events. There will also be a dust cloud. So here's an example of a dust cloud that they showed, Rossi and colleagues, that this lived on for 2 years in the system. So there might be something very long-lived. And we want to basically do polarimetric observations of this system throughout this cycle before the impact and then afterwards to basically detect how the dust is behaving. So again, with linear polarization, we can actually sort of test models of the dust cloud that is put forward from other techniques and verify that they actually make sense. And then finally, for future mission opportunities, I have just one slide. I was wondering about what to put here because there's many things that you could do and what we have planned on. But then I saw the light and it came from below, namely from the poster session, where you saw that actually I was very fond of this poster because in 2 things it mentioned asteroids and small bodies for what astronomers are interested in. And this is not very usual for us studying small bodies, I can tell you. So if we zoom up here, there's something called mini-moons that Marco already mentioned. And these are interesting for missions because they are close to us. So here's a synthetic object that we sort of did for PR purposes. And of course, because they're close, we can go there by CubeSats, which is the big thing. And this is something that even individual universities can work on. They're not too expensive for like big space missions that nobody can afford them. Well, ESA and big agencies can, but no small players. So for students, etc., this could be something interesting. And the drawback here is that while they have been discovered, we have now discovered 2, and as Marco explained, the second one was largely thanks to NOT, that did not discover it, but did the follow-up and verification that it is a mini-moon. And you cannot now see probably here, but this basically shows that when they become bright enough, so here's all the trailing effects, etc., taken into account, it's extremely short times when they are observable. So we did an analysis with the LSST pipeline and analyzing the data and found out that LSST can probably detect on the order of 1 to 5 objects per year. But then the problem is that these are not sort of the well-constrained orbits. So we need to do follow-up with something to really nail down the orbit. And what's more important, to figure out and verify that it's not an artificial satellite, because that's, of course, what we find mostly in near-Earth space. I mean, if they go around the Earth, the first bet is it's a satellite. And the way to do this is you obtain astrometric positions, and then you sort of fit an orbit with this area to mass parameter, which basically gives you an idea of how much area there is on the object compared to the mass. So if you can push, if this is high, it just shows that that's basically, say, a solar panel. It has a huge area compared to its mass, and therefore it's pushed around. If you can push that down to, say, below 1 or something along those lines, then you know that there's plenty of mass per square meter of area. So, but this takes time, and this is where NOT could, for instance, or help, telescopes like the NOT could help in this process of obtaining these measurements. And that's all. I stop there. Thanks.